Hi everyone. So in this video we begin with chapter 7, Geometry and Trigonometry. These are the learning objectives for the chapter. So by the end of this chapter, you should be familiar with finding the distance between 2 points in three-dimensional space, finding the midpoint of a line segment in three-dimensional space, computing the volume and surface area of a solid such as a pyramid, cone, sphere, hemisphere, or a solid made from the combination of these, determining the size of an angle between two lines, finding the sides and angles of a right-angled triangle using sine, cosine, and tangent ratios, applying the sine rule and the cosine rule to find an unknown length or an angle, computing the area of a triangle using the formula 1/2 AB sine of C. Solving problems involving two-dimensional or three-dimensional figures by means of right-angled and non-right-angled trigonometry. And finally, solving problems involving compass bearings. We begin with section 7.1, measurements in three dimensions. So the first thing that we have to understand is the three-dimensional plane. And here we can see an image that shows us precisely a three-dimensional plane. So we have an x-axis, which is the one we see here. We have a y-axis, which you can see here. And you have a z-axis, which is the third dimension. So how do coordinates work here? Well, they work in the same way as they would in the two-dimensional Cartesian plane. So to find point P, for example, first we travel the distance x, which is this one. Then we move in the y direction. And finally, we would go up z units to finally arrive to point P, which would be described with x, y, z. So here we are with an actual picture of a point in a three-dimensional plane. In this case, this point is 3, 4, 5, as you can see there. So that means that 3 units in the x direction, then 4 units in the y direction, and finally 5 units up in the z direction. And we arrive to point 3, 4, 5. So here are a couple of formulas that we're going to be applying to this three-dimensional geometry. For example, the distance formula. So the distance between 2 points x1, y1, z1 and x2, y2, z2 is, and notice that this distance formula is exactly the same one that we would use for the two-dimensional plane. So it's the difference in x squared plus a difference in y squared plus a difference in z squared and square root of all that. Likewise, for the midpoint, we have the same formula that we would use as well in the two-dimensional plane. Notice that we're adding the x units and dividing by 2. That would be the x coordinate of the midpoint. Adding the y coordinates and dividing them by 2 would give us the y coordinate of the midpoint. And likewise, with the z coordinates, adding them and dividing them by 2 would give us then the coordinate z of the midpoint. We begin with example 7.1, where they ask us to use the distance formula to show that 3 points F, G, and H are collinear points. So what are 3 points that are collinear? Collinear means that they have to be on the same line. So if I have point F, and this is point G, and this is point H, if they are collinear, it means that they lay on the same straight line. In order to prove this, if 3 points are collinear, that means that if I find this distance and add it to this distance, right? If I find FG and add it to GH, it should equal the full distance from F to H. Now that is logical. Just imagine if they were not collinear. If they were not collinear, then let's say this is point F, this is point G, and this is point H. Then we would have a situation where the points are not collinear. They would form a triangle. Then obviously this distance plus this distance would be more than FH. Okay, so let's start by finding the distance between FG. So FG would equal the square root. It would be then equal to 1 minus 2 squared. Those are the x coordinates, plus -1 minus 4, so -1 plus 4, and this squared, plus 3 minus 5 squared. So you have to do it in the same order. Doesn't matter if you do it backwards, but then you would have to do them all backwards. Okay, so if we do the math here, this is going to give us square root of 14. Now, let's find GH. So for GH, we would have square root, and let's say for G, 2 minus 5 squared, that would be the x coordinates, plus -4 minus, so -4 plus 13 squared, plus 5 minus 11 squared. And if we do the math here, this is equal to 3 square root of 14. And then finally, we have to find FH. So let's do FH, and FH would equal then the square root of difference in the x coordinates, so 1 minus 5 squared, plus -1 minus, so -1 plus 13 squared, plus 3 minus 11 squared. And if we do the math here, this is going to give us 4 square root of 14. And this is already proving that they are collinear, because notice that if we add these two, adding these two would equal 4 square root of 14. Therefore, points F, G, and H are collinear. So next we have example 7.2. And they tell us that given 3 of the vertices of a parallelogram ABCD, and they give us the coordinates ABC, and they ask us to determine the coordinates of vertex D. Okay, so before we do this, we have to understand a couple of things about parallelograms. The first thing is that it's standard practice to label the vertices in alphabetical order, whether it's clockwise or anti-clockwise. So notice that here we have A, B, C, and this is D, which we have to find. Now, because it's a parallelogram, this side and this side are equal and parallel, and the same thing for this side and this side being equal and parallel. Now, the interesting thing is that if you draw these diagonals, the diagonals are going to meet exactly at the midpoint. So M is the midpoint between A and C, and D and B. So we're going to use this fact to find the coordinates of vertex D. So first of all, let's find the midpoint. So the midpoint would be between A and C. That means that the coordinates of the midpoint should equal the sum of, say, we're doing A and C, so this would be 3 minus 1 over 2. That would be the x coordinate. The y coordinate would be -1 plus 1 over 2. And the z coordinate should be 2 plus 2 over 2. That means that M, the midpoint, would be then 1, 0, 2. Okay, so now let's find D. Because we have the midpoint, let's just call D X, Y, and Z. So we know that X plus the b coordinates, right? So x plus 1 divided by 2 should equal 1, because that would give us the x coordinate of D. Then we know that y plus 2 divided by 2 should equal 0. And finally, we know that z minus 4 divided by 2 should equal 2. So solving for x, y, and z, we have that coordinate D, or the coordinates of vertex D, I should say, would be then 1, right? Because 1 plus 1 is 2, and 2 divided by 2 is 1. Negative 2, because negative 2 plus 2 is 0, divided by 2 is 0. And then finally, z would have to be 8, because 8 minus 4 is 4, and 4 divided by 2 is 2. So this would be the answer. These would be the coordinates of vertex D. Okay, so here we are on the next slide, and the next slide is about 3D solid shapes. Now, in the IB exam, they expect you to be able to find volumes and also the surface area of these different 3D solid shapes, like the sphere, the cylinder, the cone, the cube, the cuboid, the hexagonal prism, the square base pyramid, the tetrahedron or triangular base pyramid, and the triangular prism. So in the next slide, we also see different names for parts of the cone and the pyramid. So notice that this is the vertex of the cone right here, a vertex. The height of the cone, all the cones that we study are going to be actually right cones. So that means that you can form a right triangle using the height and the radius, as well as the slant height. The slant height is this here. You need to know the slant height in order to find something like the surface area, for example. But then we have the features of a pyramid. So the pyramid also has a height. Now the interesting thing about this pyramid, this is the square base pyramid, is that the height goes right to the center of that base. And you also have a right triangle pattern here as well, right? With the height, with this distance, and with the slanted height, or the height of a triangular face. So next we have example 7.3. And it says that a triangular pyramid sits on top of a triangular right prism. The prism has a height h. Find the height of the pyramid in terms of h so that the prism and the pyramid have the same volume. So in this question, they're basically asking us to compare the formulas for the volume of a pyramid, a triangular base pyramid, and of a triangular right prism. So for a prism, we have that the volume of a prism is equal to the area of the base, which is a triangle, times the height. Whereas for a pyramid, you have a very similar formula. The volume of a pyramid is one third the area of the base times the height. So the difference here is this 1/3, as you can see. What that means is that in order for these two volumes to be equal, you will need to have the pyramid with a height that is 3 times the height of the prism. So then we should write a 3 here, and then we could make these equal. So that would be the answer. It means that you would have to have a height of 3h for the pyramid in order for the volumes to be equal. We will finish this video with example 7.4, where they ask us to compare a sphere and a cone. The radius of the sphere and the radius of the cone are both r. The height of the cone is 2r. Find the exact value of each ratio. So we're going to start with part A, where they want us to find the ratio of the volume of the sphere to the volume of the cone. So let's recall that the volume of a sphere is equal to 4/3 pi r cubed. And we have that the volume of a cone is equal to 1/3 pi r squared times the height. But they already told us that the height of the cone is 2r, so we can substitute h here for 2r. So let's do that. And if we have 2r, then we can rewrite this expression as 2/3 pi r cubed. So since they want us to find the ratio of the volume of the sphere to the volume of the cone, then what we have to do is divide. So 4/3 pi r cubed divided by 2/3 pi r cubed, and this obviously will give us 2. So that means that the ratio of the volume of the sphere to the volume of the cone is 2:1. Okay, so I'm going to erase this, and we're going to do part B. Okay, so now let's do part B. So for part B, they want us to compare the ratio, or they want us to find the ratio of the surface area of the cone to the surface area of the sphere. So let's start with the surface area of a cone. So the surface area of a cone is equal to pi r squared. That's the surface area of the base, which is a circle. Pi r squared plus pi r times L. Now L is the slanted height. But notice that because this is the height here, and the base of this right triangle is r, we have that L, the slanted height, is actually equal to the square root of h squared plus r squared, which is the Pythagorean theorem. So let's substitute that there for a second. And let's rewrite it as square root of r squared plus h squared. But again, h is equal to 2r, so I can substitute h for 2r, and that would then be 2r squared. But this expression here can be simplified, because this would be then the square root of r squared plus 4r squared, and this equals square root of 5r squared, and we can simplify that as r square root of 5. So notice then that in reality, I can rewrite this thing as, and I'll do it here, I can rewrite it as r squared square root of 5. So the reason I'm doing this is because I want, of course, a simpler expression in terms of r only. All right, so now we want the surface area of the sphere. And that one's easy, because it's simply 4 circles, 4 pi r squared. Now, let's find the ratio then between the surface area of the cone to the surface area of the sphere. That means that we have to divide this surface area by this surface area. We can do a little more simplification here. Notice that we have a common factor, which is pi r squared. And that times 1 plus square root of 5. So let's rewrite it as that. So then the ratio would be surface area of the cone over surface area of the sphere. And that is going to be pi r squared times 1 plus the square root of 5, and all of this over 4 pi r squared. So notice that this cancels out, and I'm left with 1 plus square root of 5 over 4 as the ratio of the surface area of the cone to the surface area of the sphere.